begin with a word of prayer. Dearly Father, we thank you for this day. I just pray that you just help us to use it to your glory, Lord. In your name I pray. Amen. Okay, so I'll collect your homework. Go ahead and hand it over. I'll get it. So did you guys figure out the ellipse one? Was I right in my conjecture that the A's cancel?
Yes.
Yes.
I mistakenly wrote 1/2 instead of 1/A as a constant.
Yes. Yes, unless A equals 2, that will not help you. Right? Let's see here. Thank you, sir. Did you have one?
Yeah.
Oh, you already? Okay, cool. Thanks. Alrighty. Okay, so we're broadly speaking in chapter 10, except when we're not. And what I mean by that is I'm introducing a little material from chapter 13 to help guide us in our conceptual overlay here. And the basic point is this, is that in chapter 10, he only talks about x and y as if they're independent, even though they're not. But in fact, x and y are connected. They're the x of t and y of t. These are two different parts, right? So what I'm trying to tell you is that the parametric view of curves is wise to view with vectors. So what are vectors? I mean, I introduced this last time. Just notation though, right? I told you R of t equals to like f of t, g of t was a, for t in some domain, right? That this is a parametric description of some curve in the plane, right? And so like in chapter 10, he wouldn't write that, right? Your book would do what? He would just say, well, I'm not going to bother with this. I'm going to instead just tell you guys x is equal to f of t and y is equal to g of t. And that's fine. He can do that. But really, you should understand that x of t and y of t are part of a pair, this f and g in my hypothetical example here. They go together to parameterize the curve. So just for an example, just to get us started here. Let's see here. We could have something like r of t equals to, I don't know, how about 3 cosine t, 2 sine t for t in 0 to 2 pi, right? This would be a parameterization of what curve? Well, let's just think about it kind of in terms of what you know about sine and cosine. What happens to sine and cosine as they range from 0 to 2 pi? They go from what? From -1 to 1, right? So 3 cosine does what? It ranges from 3 to -3, right? And 2 sine t goes from -2 to 2, right? And so if you think about it, like, and you could plug in some points, right? And if you plugged in some points, what you would generate, if you make that table of values like we did last time, so your x would go between like this point and that point, right? When t is equal to 0 or pi, your y component's 0, and you get these points, right? Like 3, 0, and -3, 0, right? And let's see, when t is equal to pi over 2, what do you get? You get the x component 0, the y component's 2, right? And when t is equal to 3 pi over 2, you're down here, right? Let me just mention, okay, so this would be t equals to 0. This would be t equals to pi over 2. This would be t equals to pi. Over here, you're looking at t equals to 3 pi over 2, right? And what happens if you throw in more values? What do you think? What if we look at like pi over 4? Where's that? Pi over 4, cosine of pi over 4, sine of pi over 4, it's about 0.7, right? So you're about 70% this way and about 70% that way. It's like up here somewhere, right? Give or take. And likewise, there's a point down here, and there's a point over here, and there's a point over... You starting to see what it is? And you add more points, what do you get? Oops, I can't draw. What do you think it is? It's a circle. Right, and it's an ellipse. Looks like an ellipse, right? Now, how would we convince ourselves of that? What's the equation of an ellipse? It has the form what? Right, now that's why I covered that conic section, so that you have that on your brain, right? So you remember that now. And, okay, so let's see here. For this problem, we have what? We have x is equal to 3 cosine t, and we've got y is equal to 2 sine t for our parameterization, right? And so what do you think how can we show that this parameterization in fact does parameterize that ellipse? What do you do? What I do personally is I go, okay, well I know cosine squared t plus sine squared t is equal to what? That's equal to 1, right? So if you look at that, that's also what? That's also 3 cosine of t squared, right? Divided by 9, or 3 squared if you like, right? And then plus what? 2 sine t squared divided by 2 squared, right? So all I did was I just introduced 3 squared over 3 squared and 2 squared over 2 squared, right? I can do that. And then what do I have? This is exactly, you see this is exactly the x, right? This is exactly our y. And so what I have then, of course, is x squared over 9 plus y squared over 4 is equal to 1, right? In other words, we've shown that the parametric equations are mapping into the solution set of that Cartesian equation. So there you go. In fact, it is an ellipse. In fact, it's an ellipse with major, like vertices 3, 0, minus 3, 0, 0, 2, and 0, minus 2. Does that make sense? Now that I've done this example, right, I bet if I asked you to parameterize a follow-up example, I'm eventually going to get back to vectors, but we're on a roll here, so let me stick with it for a minute. Parameterize. I'll do 2 more examples. Parameterize ellipse x squared over a squared plus y squared over b squared equals to 1 for y greater than or equal to 0. So let's see here, what should you do? Set x equal to what? What's that? X is cosine t. Well, a cosine t. Yes, a cosine t is what we want. So you let x equal a cosine t, and you let y equal b sine t. Yeah. Okay. Kind of loud. Let's see here. So we're just trying to get this part of the ellipse, right? Right, we just want this part of the ellipse. So what range of t do we want to let be the parameter domain? I'll start us out. 0 less than or equal to t, less than or equal to what? T equals 0 produces a comma 0 if you plug it in, right? Cosine of 0 is 1, sine of 0 is 0. How do I get to minus a0? Put t equal to what? Pi, yeah. Of course, geometrically, you can see what's going on here, right? In fact, t is just the polar angle, right? So there you have it. What if we had this? Parameterize x squared over a squared minus y squared over b squared equals to 1 for x greater than or equal to a. What would you do? Ball's in your court. Let x equal to blank and y equals to blank. You guys fill in the blanks. I'll tell you which parameter domain. We'll let t be any real number. I'm assuming a and b are positive constants in both of these examples, okay? That's usually assumed in these sorts of problems, whether it's stated or not. It should be stated, but I am assuming a and b are positive constants. A cosh, I like it. Go, listen to me. Come on. A cosh t, right? And b, and y equals what? B sinh. Indeed. Let's see. Is she correct? Let's try it out. X squared over a squared minus y squared over b squared for our parameterization is equal to what? A cosh t, quantity squared, divided by a squared, minus b sinh t, quantity squared, divided by b squared. Right? So to check whether or not your proposed parameterization actually works or not, we plug it into the formula and see if it actually does land on the hyperbola as advertised, right? And I think we have a winner because the a squareds cancel, the b squareds cancel, and we're just left with what? Cosh squared minus sinh squared equals 2? Well, that's 1, right? So there you have it. In fact, that is now the rest of it, like how do I know it covers that part of the ellipse? Notice, right? A cosh t, right, is greater than or equal to a times the cosh of 0, right, which, by the way, is equal to a. Cosh of 0 is 1. That's the smallest value that cosh takes. We know that from our study of hyperbolic cosine before, right? So, in other words, x is greater than or equal to a for our path. Again, just to emphasize, the x and the y are not disconnected. We can view x and y as part of what path? We have r of t is what? A cosh t. Oh, I'm sorry, I'm getting too carried away. Sorry. I'm going to talk about one example at a time here. Oops. So this one, we have what? We have path r of t is a cosh t, b sinh t, and this one we have the path r of t is a cos t and b sin t. All right. Any questions? All right. So vectors. Let's talk about vectors for a little bit. What are vectors? So we're just talking about vectors in the plane. So basically a vector in the plane is just a directed line segment, right? It's something like, you could view it like this, right? This would be a vector A. This would be a vector B, right? And if you want to think about it, you can identify these with like A1, like A1, A2, and B1, B2. How would you do that? What's the idea? You just, think about the coordinate axis, right? Here's our XY coordinate system. And all you do is you take the vector, right? And you do what? You move it down to here, right? You move B down to here. And that point that it points to is exactly what? This B1, B2. So there's this natural correspondence between directed line segments from the origin, right, and actual points in the plane. We make use of this correspondence whenever we talk about vectors in usual applications of calculus. And likewise, this vector, I can move it here, right? Down to here, like so, And so like A points to that point right there, which is also A1, A2, right? Sometimes, guys, I'll write angle brackets to emphasize it's a directed line segment. Like if I want to distinguish between the point A1, A2 versus the directed line segment, I will use this for the directed line segment, whereas I'll use that for the point. But I'm identifying the two. Like I'm not making a distinction between those two things. I'm going to add them together, and mathematically they're for us the same. So anyway, enough about that. How do you add vectors? So if I have, geometrically, the way it works is you go like tip to tail, right? So here's A, here's B. You just draw them like that, one after the other. And if you think about this, right, it's not hard to see that the so-called resultant vector, this one I've drawn in blue, A plus B, has what? What is it in terms of A1 and B1 and A2 and B2? It's just what? What's this point up here? A1 plus B1, comma? Very good. I'm an idiot. A2 plus B2, right. So you add the y components and you add the x components separately, and that's all there is to it. All right. And there's also something that's defined as, there's also what's called a scalar multiple. So like if I have C times A, this is defined to be CA1, CA2. So-called scalar multiple. Now, an interesting case of that is what happens if you put C equals minus 1 as an example. What's C equals minus 1? Scalar multiple by minus 1 does what? Like minus A is over here, right? For what it's worth. And that makes sense, right? If you add the red vector minus A to the black vector A, where do you get to? Yeah, you go nowhere, right? Out. So if you add this vector to that vector, right? In other words, put the tail of minus A to the tip of A, you go like this and then back again, so you're just at the origin. So of course, A plus minus A should be the 0 vector, right? Which is the origin. Nothing particularly shocking here, I hope. Yeah, that's how you add vectors. All right. The other fundamental thing you want to know about a vector is its length, right? So what's the length? So sometimes we use this notation, or sometimes we'll just say A like this without the vector is the length, the magnitude of the vector. What's that equal to? It's the same as the distance from the origin, right, that the point it corresponds to. It's just what? The square root of a1 squared plus a2 squared. I believe you guys know that, and you're just not telling me. I could be wrong, but I, in my heart, believe there's someone here who knows this and just doesn't like to talk. That's fine. All right, we also have the dot product. What's the dot product? Well, you can introduce this dot product. It's a dot b. It's a way of taking two vectors and getting a number. The number is simply this, a1 b1 plus a2 b2. So you multiply corresponding x components, and then you add the multiplication of the corresponding y components. This is the dot product. All right. What good is the dot product? Well, uses, has many uses. For example, what happens if we look at a dot a? That's a1 squared plus a2 squared, right? Because it's a1 times a1 plus a2 times a2. What is that? That's equal to the length squared, right? This is the length squared. So we have a formula for the length. We could write the length as the square root of a dot a. That's another way you could express it. Fine. Let's see, what is the other popular use of the dot product? Well, the other really important thing to know about a dot product is there's a theorem, and this theorem is by no means trivial, which is that a dot b is ab cosine of the angle between them. So this theorem here is essentially equivalent to the law of cosines. So that's like an algebraic way of writing the law of cosines in vectors, more or less. And, so if this is A and this is B, this is the angle between them, theta. That formula tells you how to figure that out. I'll tell you what, I'll do something with numbers for a second here. How about if A is 1, 3, and B is equal to, I don't know, 5, 10. What would the length of A be? What would the length of B be? Square root of 10? Square root of 125. Because 25 plus 100 is 125, and 1 plus 9 is 10, right? What's A dot B here? One times 5, right? Plus 3 times 10. What is that? 35, right? So if you believe the theorem, and I encourage you to believe it, 35 is equal to the square root of 10 times the square root of 125 times the cosine of the angle between these vectors. Now, I know you guys could write those vectors in the Cartesian plane and do right triangle trigonometry to figure out the angle, right? Wouldn't be a big deal. My point to you is I don't have to, and I can find it with absolute certainty. That's what I'm doing right now. So the angle between these vectors is the inverse cosine of the ratio 35 divided by the square root of 10, square root of 125, which is what? Yeah, I don't know without a calculator. Sorry. While I'm getting my calculator out, the beautiful thing about what we're doing right now is, well, of course we won't do it because we don't need to. This business I'm doing right now is also true for three-dimensional vectors, or 4, or 5, or n-dimensional vectors for that matter. 8.13 degrees. So which probably makes sense if you draw a picture, right? 1, 3 is what? Over 1 up 3, roughly speaking. And this is over what? Over 5 up 10. I can't draw it worth anything, but you can tell, right? Anyway, my point is I'd have to actually find that with right triangle trigonometry, I'd actually have to do some thinking. Here I can just calculate. If you know about the dot product, it allows you to find angles between line segments in the plane with terrible efficiency. Terrible in the good way, like sick. But not sick, right? But sick in the good. I don't know. You guys don't say sick anymore, so I don't know what I'm talking about. That's like so 2009. Let's see here. All right. Anyway, I'm trying to not say too much about vector. I'm just trying to give you just a brief introduction to vector algebra. This is the main thing we use geometrically in physics, right? All right. So that's about all there is, just algebra-wise. I mean, you can talk about basis and other things, but that's enough for us in here. What we're really interested in is not just vectors which are static vectors like 1, 3, or 5, 10. We're interested in vectors of functions, right? Because vectors of functions are paths. Vectors of functions of t are paths, right? So if you think about it, like r of t, right, is x of t, y of t. That's a vector of functions. But I could just as well write it like this, like a of t is, a1 of t, a2 of t. And you can add vectors of functions, and you can scalar multiply vectors of functions. You can even take the dot product of vectors of functions, all just the same. All right? How do you differentiate a vector of functions? What is dA dt defined to be? Now, I hope you guys are really awake. This is very difficult, what I'm about to do. So focus. I hope I have not lost you. This is how we do it. All right. I know it's very dangerous that I'm doing this in Calc 2 instead of Calc 3 because this is a Calc 3 topic, and I know you guys aren't in Calc 3 yet, so maybe you're not ready for this. But this is how you differentiate a path. I mean, come on, it's easy, right? Okay, you just differentiate component-wise. And there are beautiful rules. The properties of the calculus of paths are just the simplest thing you could hope for. They're just nice. So here's the properties. Properties. Good job. Put 2 O's in properties. Properties of the calculus of paths. All right. Just a quick rundown. If I have d dt of a sum, guess what? It's the derivative. It's the sum of the derivatives. Nothing terribly surprising there. This one's a little bit surprising. If I take a function, all right, times a vector, all right, so f is a function, you get a kind of product rule. What you get is the ordinary derivative of f times a plus f times the derivative of a. You also have a product rule for dot products. If you took physics with me this semester, I showed you how this dot product rule allows us to derive things like acceleration being mv squared over r for centripetal motion. This is a very important product. It allows you to see many things. I suppose I'm allowed one more comment about the dot product. What's the significance of the dot product being 0? I should have said something about that. What does it mean when the dot product's 0? If this is going to be 0 and A and B are non-zero, what does that force the cosine to be? 0, right? Which means the angle between them is? No. 90 degrees, right? Pi over 2. So if you want to characterize when vectors are perpendicular, just check if their dot product is 0, and that tells you that. Anyway, I hope you study the Fresnel's theory of curves next semester. If you do, you'll find that this dot product is very revealing about many geometric things. But anyway, anything else? What happens if f is a constant? If f is a constant, that second rule simplifies, right? df dt is 0, and what you get is just that you can pull a constant out, right? Likewise, if one of these is a constant vector, basically this rule simplifies to saying you can pull a constant out of the dot product as well, in some sense. All right, that's all I have to say for this part. I'll bring us back. So consider then r of t equal to x of t, y of t. In other words, a path, all right? We know that if we allow t to range over things, that traces out a curve, right? We're looking at a parameterization of a curve. The collection of points that this thing hits is a curve, all right? We can define something from this. The velocity, v of t, is equal to, now hold on, it's really complicated. Oh, I'm sorry, I already told you guys. I mean, we already got past this. I'm sorry. So, but it's exactly, oh, I'm sorry, I've defined it. Well, it's dx dt y dt. In other words, I should have written this other thing first. Oh, well, I already wrote it. You know, it's just dr dt, right? But velocity is a vector. Just like the path is a vector. The path is, we also call it the position in physics, right? Now, when we're talking about a physical particle, we'll say it's the position at time t, right? But I don't want to put that on us in here because a path doesn't have to correspond to the physical position of some particle in here. It's just a mathematical thing we're studying, right? T doesn't have to be time. It could be something else in principle. Anyway, that's the velocity. What's the magnitude of the velocity? I'll give it its own definition. The magnitude of the velocity, right? In other words, the square root of v dot v, which you could write as what? The square root of dx dt squared plus dy dt squared, right? That's just the length of the velocity vector. This is called the what? Called the speed. So the speed is the magnitude of the velocity. The speed is a scalar. You guys with me? What I want to show you, or I'm going to try to argue for you anyway, is that, in fact, we can show for smooth curves, at least, v, which is, by the way, this is also denoted v, right? If we drop the vector and just write v, that's the speed. Sorry. You can also write that v is ds dt, where this is where ds is the infinitesimal arc length subtended in time dt along the path. Here's a picture. Here's the curve. I've parameterized this curve with a path. All right. I want to study like two very close by points. And I'm going to give you a somewhat sloppy, infinitesimal argument to start with, and then we'll make it better. I may make it better next week. I'm not sure if I'm going to do it for you guys today, because I'd like to do an example with numbers also today, so we might not have enough time for both the full theoretical justification and the example today. So I may just kind of give you the heuristic explanation today and give you the rigorous one Monday, perhaps. But suppose this is R of t, all right? This is what you could say R of t plus dt. Like, think about just a little bit more time, right? So what, with this vector here, connecting them would be what? I tell you what, that dt I just wrote is making some of you uncomfortable, with good reason. Let me make it delta t. There you go. A little finite increment of time. Then this right here, right, we could call the change in the position from this point, right, to this point on the path. And what would that be? That would be equal to r of t plus delta t minus r of t. Now, you might not believe me, all right? But you can see that from vector addition that I was talking about a minute ago. If you take, let me say this blue vector, let me make the bottom vector a different color so you can see it better. All right, so the blue vector plus the purple vector, right, should be equal to the pink vector. Agree? Can you see that? If I add the blue vector and then tip the tail, the purple vector, right, that's the same as the pink vector. The pink vector is r of t plus delta t. And you can see that's what I have. R of t plus delta t is equal to this plus that. Right? So then what do I do? Well, you take this and you divide by delta t. What's it give you? Delta r over delta t is equal to r of t plus delta t minus r of t divided by delta t. Right? And so what happens as delta t goes to 0, what do we get? We get that delta r over delta t is equal to what? I mean, it should be the velocity, right? But on the other hand, you can say, in other words, basically the velocity is equal to approximately delta r over delta t, right? If the delta t is small enough, right? And what's that give us? That gives us that the velocity times delta t is equal to delta r. So take the magnitude of both sides. What's the length of this? Well, the length of this is exactly the speed times delta t, right? What's the length of that? Well, the length of that is just the length of the purple vector, right? mean, it's the length of the purple vector. That's all I really want to say. What's more interesting, right, is that it's very, very close to what? The length of this curve right here, right? So the length of the thing, the ds thing, has length ds. So it's approximately equal to delta s, you could say. So anyway, in the limit, you get that v dt is equal to ds, or simply that v is equal to ds dt. So the speed is the change in arc length per unit time, the infinitesimal change. And you can make this more rigorous, all right? I will give you a annoyingly rigorous argument for it some other day, okay? Not today.